Hello, Logic fans. This morning, I'm going to be introducing you to our 4 rules that are in Chapter 19, along with our special 5th rule, Destructive Dilemma, that is not in our book, and I am not requiring anyone to use, but it is sometimes useful, and I want to give you the option to use it if you so choose. The rules that I'm going to be covering today were all covered in Monday's class from November 23rd, and they are conjunction, simplification, addition, and constructive dilemma. And then that 5th one is called destructive dilemma, which is a variation of constructive dilemma. This video is going to be fairly short and to the point. I'll explain a little bit of, I'm going to start by just showing you the rules as they're presented in Chapter 19, and then I'm going to talk a little bit about the differences, things to watch out for, and so forth. Okay, so first of all, conjunction. It is, looks like this. It is abbreviated CONJ. Conjunction starts off with 2 lines, very simple, P and Q. And so like on any premise, any 2 premises, essentially what it's saying is that you can take any 2 premises, the whole lines, put them on the same line and combine them with an and only an and, not any other symbol, not any other operator. And the reason why this works is, remember, each premise is simply saying something, it's asserting something as true, and which means that you can read premise 1, P is true, and Q is true, and all the other premises are true. So you can take any of those premises, and you're essentially just putting those premises on the same line, saying premise 1 is true and premise 2 is true. We're going to consolidate them and call that a new premise. That's essentially what conjunction is. And as a reminder, P, Q, this applies for all rules. P can stand for any well-formed formula, any statement, no matter how complex. All that matters is that you have to take the whole line. When it says P like this in a rule, you have to take the whole line and abbreviate that, abstract that as P. Okay? So if I had, for example, A and B on line 1, and if E, then not F on line 2, I could use conjunction to go like this, A and B, and if E, then not F, okay? And what I've done is I've taken the whole premise 1 and the whole of premise 2 and simply placed them on the same line combined with an and. It can't be any other symbol, any other operator. Next, let's look at simplification. Simplification, this is, I actually should have started with this. Doesn't really matter, but this is how it's laid out in the book. Simplification, okay. And this is usually abbreviated as SIP. Simplification is quite simple. It's basically the opposite of conjunction. You start with 1 line that has a conjunction as the main operator. It must have a conjunction, an and is the main operator. This doesn't work with any other operator. None of these rules do. All the rules, whatever operator is in the rule, that rule must be in the argument itself. There are no substitutions unless the rule specifically lists those as substitutions, and we haven't seen any of those yet. Anyway, simplification only requires 1 premise, P and Q. And what this line is saying, of course, is that P is true and Q is true. They're both true. There's no other possibility. P must be true. Q must be true. Based on this, we know that P is true on its own. That's what the and means, is that both of them are independently true. So we can simplify this. Again, this must be the full line. So this is something that I see people, an error that I see people make, is that they see something like if A, then B and C. and they think, well, oh, I see the and here. I can just simplify that and go like this. That is not valid. That is not a proper use of the rule, because here the main operator is a conditional. However, we need the main operator to be an and. Since this and is not the main operator, you cannot use simplification. Likewise, I've seen people use simplification on something like this and say, well, if this is true, then this must be true. No, definitely not. That is definitely an invalid move. Not only, so this is not an and, but let me just go in a little deeper on this. This line here doesn't say that A is true. This line says that if A is true, then C is true. You can't conclude that A is true. For example, we take the sentence, if it snows outside, then you should wear your snow boots. Okay. You may not agree with that, but you understand what that means. It doesn't mean that it is snowing outside, right? It's just saying that if it snows outside, then you should wear your snow boots. You can't take that sentence and then conclude that it is snowing outside. It has to be an and, must be an and. All right, moving on. This next one is addition, and I feel like no matter how many times I say this, it never hits home. But this one is the most counterintuitive. You're going to look at this and be like, oh, that's simple, I get that. And then when it comes time to use it, everyone's like, even the people who are really locked into this stuff and who learn it quickly, they almost always are like, I don't understand why that makes sense. It's counterintuitive, but you'll get it. And when you do get it, it'll make literally everything make more sense. Addition only requires one line to begin with as well. And it can be anything. So we'll just say P, because P can stand for anything. Again, it must be the whole line. As all of these rules, the line must be the whole line. If P is true, then P or Q is true. Right? Seems pretty basic, right? Make sure you notice what's weird about this. In every other rule that we have used, that we have looked at, in every other rule that there is for this, all the letters that are in the conclusion are pulled from the premises. So we take, as an example, hypothetical syllogism. If P, then Q. If Q, then R. Therefore, if P, then R. Like this R comes from here. This P comes from here. We lose the Q, that's fine. But we must get our conclusion from the premises. In conjunction, this P comes from up here. The Q comes from right here. Here, we lose the Q, but the P comes from this P. Like every other rule, modus ponens, modus tollens, disjunctive syllogism, whatever, the conclusion comes from the premises. This is the only rule where we literally, it feels like we are getting a letter from nowhere, and we are getting a letter from nowhere. You can add any letter you want. Now, if you're tuned into logic, you're like, well, that doesn't make sense. Logic is supposed to be logical. If you have a premise, you can't just conclude made up stuff. That's what it feels like. I get it, because the first time I learned this, I was like, why does that work? It works like this. Remember what P or Q means. P or Q means that at least one of these is true. Either P is true or Q is true. Maybe both, right? Now, if P is a premise, and it must be for this rule to work, then we have established that P is necessarily true. So if he has established that P is necessarily true, then this sentence is necessarily true as well, because the P is true. Well, what about the Q? It doesn't matter. Q might be true, it might be false, but it doesn't matter, because in order for this sentence to be true, the only thing that's needed is the P to be true. That's the end of the story. What's really critical here is that you have the or. If you have any other operator down here, it won't make sense. Certainly not the and. Like if you did this with an and, if you concluded P and Q, then you actually would be making stuff up, because now suddenly you are declaring that Q is true, and you didn't have any reason to say that Q is true. But here, we're not actually saying that Q is true. When we do this, addition is not claiming that Q is true. It's not providing any indication that Q is true. There's no like small amount of support that Q is true. It's only recognizing the possibility. And that's not the same thing as evidence. It's not the same thing as indication. Okay. So that's addition. And in some of the practice problems we'll use, I'll make sure to use some practice problems with that use addition so we can talk about it. Last thing I'll say about this is that please come to class with questions about this. Like when you do the practice problems and you find difficulties, bring them to class and we can talk about them. That's the way to get better. Next. Let's look at the last rule that's in our book in chapter 19. Constructive dilemma. And this one's abbreviation is simply CD. Constructive dilemma is kind of like a double modus ponens. And so remember modus ponens. Modus ponens goes like this. If P is true, then Q is true. P is true, therefore Q is true, right? So line 1 doesn't say that P is true. It just says that if P is true, then Q must be true. You combine that with line 2, which says P is in fact true. Because P is in fact true, it forces Q to be true. Therefore, we can conclude Q. Constructive dilemma works like this. If P is true, then Q is true. And if R is true, then S is true. So we just have two different conditionals on the same line. And by the way, these, based on the way our book describes it, these don't even have to be on the same line. They can be on different lines. Because of conjunction and simplification, they're the same thing. Line 2 goes like this. P or R. Then the conclusion is Q or S. So let me just talk a little bit about why this works the way it does. So remember that modus ponens, if the P is true, it forces the Q to be true, right? Here we have, it's like we have that first line of modus ponens repeated twice. And because they have different letters, it just means that it can be, different letters in our argument. Now line 2 doesn't have a single letter. It has P or R. Notice that this disjunction has the two letters that it must have are the antecedent of both conditionals. It has the if part of both conditionals. That must be the same. That is a critical feature of this rule. Then, get some coffee here. Line 2 doesn't say that P is true, right? And it doesn't say that R is true. The only thing that it's saying is that at least one of those is true. Maybe P is true, maybe R is true. One of them must be true, maybe both. It's that inclusive or. So hypothetically, if P is true, that would mean that Q is true. So there's a possibility that Q is true, but not necessarily. Maybe R is true. If P is not true, then R must be true. And if R is true, then S is true. That's our S. So in other words, if at least one of these is true, if either P is true or R is true, then it also is the case that either Q is true or S is true. Because essentially what we're doing here is that we have two, it's like we're laying out two modus ponens next to each other, and we just don't know which one has an affirmed antecedent, but we know that at least one of them does. And because we know at least one of them has an affirmed antecedent, we know that at least one of them has an affirmed consequent, their Q or S. And that is constructive dilemma. Okay. Finally, we'll do the bonus rule. And I'm going to leave constructive dilemma up for this because it's a handy reference. And then after I do destructive dilemma, I'm going to just show some tips. The last rule we call destructive dilemma. Destructive dilemma easily has the coolest name in any, like if logic was a video game, destructive dilemma would be the main boss for sure. Constructive dilemma would be like your helper or whatever. Destructive dilemma is like, I'm going to destroy you. Anyway, I'm a nerd. So destructive dilemma is the mirror image of constructive dilemma, in the same way that modus ponens is the mirror image of modus tollens. Remember, so modus ponens, if you know what, let me write it out like this. Okay. Modus ponens is like constructive dilemma. Constructive dilemma essentially uses modus ponens. Destructive dilemma uses modus tollens. If P, then Q, not Q, therefore not P. Okay. Now notice with modus ponens and modus tollens, they both have the same first line. The key difference is that where modus ponens affirms the antecedent, modus tollens denies the consequent. As a result, it also denies the antecedent, right? That's how modus tollens works. So destructive dilemma, just like this, everything is an analogy here. Everything's analogous here. Line 1 is going to be identical to constructive dilemma. If P, then Q, and if R, then S. 2. Instead of affirming the antecedents in a disjunction, we are going to affirm or deny the consequence of each conditional. Okay. So see, the critical feature here is that it denies the second part of each conditional. If Q, we don't know if this is true. We don't know if not Q is true. We don't know if not S is true, but we know that one of them must be true. If not Q is true, that forces P to be false. It's just this. It's like we don't know that this one is the case, but if it is the case, then it forces P to be false. Likewise, here, not S, it forces R to be false. And that is destructive dilemma. So again, this rule is not in your logic book. It is not in the Hick logic book or the Herrick logic book. There are about a half dozen big logic textbooks out there, and almost all of them include destructive dilemma. Why doesn't our textbook include it? I don't know. Probably because the author thought it was unnecessarily complicated. And it is true. There is something to that, we as logicians, we want to have the fewest number of rules so that they have the greatest amount of applicability. I don't know if that makes sense, but it's like, think about a recipe book. Think about a cookbook that allows you to cook, 500 things with 7 different ingredients. Like, that's pretty awesome. That means that the only thing you ever have to get are 7 different ingredients. And then depending on what you want, you can combine those 7 different ingredients, do different things with those ingredients, and get 500 different recipes. That's kind of different than a cookbook We might say maybe a more advanced cookbook, or a cookbook that requires a fancier kitchen, that requires, we might say that some cookbooks have 1,000 different ingredients in them for, 500 recipes. If a cookbook has that many recipes, you probably can't cook all the things in that cookbook with what you have in the cupboard. It becomes less versatile because of the diversity of ingredients that it requires. So in a sense, what we're trying to do in logic, and the same thing is true in computer programming as well. Like, you think about, like, computer programming is all based on this. And in computer programming, it all comes down to actual, not just the computer languages, but the actual, little wires and the switches and the, I forget all the terminology, this is not obviously not my field, but it all comes down to wires and logic gates, the way they're built. And we can only build so many different kinds of logic gates. We can only put so many in your computer. So it's like your computer, especially when we want smaller and smaller computers, like in your cell phone or your smartwatch or something like this, these microprocessors. We want to include the fewest number of tiny machines that can do the greatest variety of things. So it's like some ingredients in your kitchen, going back to the kitchen analogy, some of your ingredients do the heavy lifting. Like, we find some ingredients in almost everything, salt and pepper, right? Like that, those two are in almost every recipe. Whereas other ingredients like saffron or okra are relatively rare. So like, maybe one way of talking about this is like, destructive dilemma is like the saffron of your kitchen. You don't need it. There are other ways to replicate that flavor. I mean, there's no way to replicate saffron, but in logic, that's where the analogy breaks down. But there are other ways to imitate destructive dilemma within logic. And in your computer, we want to be able to have the fewest number of machines that can do everything, like to play video games, to do art, to let you write your paper, to let you surf the internet. If you can do all of that with 5 different mini machines, fantastic. You don't want to build more machines. And a large part of what the computer industry has been about over the past, what has it been, 80 years now, since the first computers were sort of invented during World War II. A little bit, yeah, about that. We want to build a small rule set that can do an infinite number of things, which is why, going back to my earlier point, perhaps our book's author, Herrick, chose to leave destructive dilemma out because he saw it as a unnecessary ingredient, whereas other books see that, there's a fuzzy line here where a lot of these rules can in fact be reduced to smaller, simpler statements. How many rules do we actually need to prove an argument? Probably like, I don't know, 3, 2, 1 maybe. And that they're all sort of variations of complex structures. And the reason why you want more is to be able to give you some more speed, because, I probably don't need to continue explaining this, but there's just a balance to be struck. The fewer number of machines that you have means the smaller and smaller of a physical space you can build your computer, and the more things that can do based on a smaller set of rules, if those rules are chosen well. But the disadvantage of that then is that we have taken complex processes and divided it up into many simple parts, which means that the process takes longer to go through. The equivalent of our rules is this. Every rule that we add is something more that you have to memorize, something additional that you as a human being needs to learn. That is a tax on our brain. That is a tax on our human computing power. But if we reduce the number of rules, and we said we only have to learn one rule, and I'm going to teach you how to apply it to everything, then the process of solving any argument becomes incredibly tedious. I mean, that's essentially what the truth tables are. So yeah, that's my kind of introduction to the 4/5 rules, and a little bit of talk about why we would or would not include a rule. Bottom line is, you can use it if you want to, but I will never give you an argument that it mandates that you use it. Okay, so that's all. I'm going to make another video in a moment here to give you examples of proofs. That's it.